So we have three charges at the corners of a rectangle, and they're all positive. In part A, each of these guys is a positive charge. Now let's give them numbers just so we can talk about it. I like doing that. Let's say that this guy, charge 1, charge 2, charge 3. Now what we're asked to find is the net electric potential, the electric potential at the upper right-hand corner, right here. Okay? What's the other thing that you could be asked to find that would be much more difficult? And it's from last chapter. Electric field, right? If you think back to what we did last chapter, the question was find the electric field. So I want to mention this just briefly because, you know, on an exam, you could be asked to find the electric potential, which is what we're going to do here, or you could be asked to find the electric field. Which one of those is much more difficult? The electric field, and here's why. You know, electric fields are vector. Okay? Electric fields are vector. Electric potential is scalar. Now, why is this? Don't just memorize this. Well, think about it. What's the definition of an electric field? If you look at the basic definition for an electric field, it's force per charge, right? And if you take that equation and rearrange it, you get the very familiar F equals QE. Remember that? QE, just like in the gravitational field, it's mg. I wrote a very famous song about that. Okay, so look, why are electric fields vector? Electric fields are vector because it involves what? Force. Does force have direction? Sure does. Force has direction. Now, what's electric potential? The definition for electric potential, which is capital V, what's electric potential all about? Potential energy per charge. It's volts, not to be confused with volts. Okay, don't confuse that with volts because you just wouldn't want to do that. So look, does energy have a direction? No. It's, you know, you eat 500 calories of breakfast. Can you put a direction on 500 calories? No. I ate 500 calories south. So electric potential is scalar. I want to get into I'm kind of like rambling a little bit, but it's good rambling. This is important stuff. So electric fields, vector, electric potential, scalar. So just as a review, real quick, what if this question wanted you to do electric field at this point? What you'd have to do is go like this. You'd be like, all right, positive charge, electric field goes where? Out. So what's it doing at our point? For charge 1, it's going out like that. Remember this? E1 like that. Okay, charge 2 is plus, out in all directions, right? So it's going out like that. That'd be E2 at that point. Then charge 3 is plus. It'd be going boom, up like that. Okay, then what's the equation for electric field? K, Q over R squared. So you'd find E1, E2, E3, like 3 separate calculations. You'd have to figure out this theta, and then the rest of the problem would be vector. Figure out your total x, your total y, Pythagorean theorem. That's how you would do electric field. Now, watch how to do this problem. So what do they want in that upper right-hand corner? They want the what? Electric potential. Much easier. Now, what's the equation that we're using? If you have a point charge, right? Electric field's going out. If you want to calculate the electric potential at a distance from the charge, so here's Q, what's the equation for finding electric potential at a distance from a charge? K, Q over R. It's almost the same equation for electric field. Notice that the Q is not absolute value. That's important. If a charge is negative, you got to plug it in as negative. Okay? So let's do it. So we go to this point right here. So let's call this guy, they're all positive. Positive, positive, positive. So this guy 1, 2, 3 like this. Okay, so we go to this point and we're going to be like, all right, the electric potential there is going to be KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. It's the algebraic sum, no vector stuff at all. Just add it up. Okay, you know what I do? Let's factor out the K. It'll make it easier. Let's pull this K out just to make the algebra a little easier. Put a parenthesis here. Like that, put the K outside. All right, so here we go. So we're going to have K, which is 9 times 10 to the 9th Newton meter squared over Coulomb squared. Okay, Q1, this guy right here, micros, be 8 times 10 to the negative 6 Coulomb. Bam. Now what's the distance from him over to that point? 0.06 meter. So 0.06 meter. Okay, plus, okay, go to Q2. 2 microcoulombs. 2 times 10 to the negative 6. What's the distance here? You're going to go do. You got to do a little bit of trig. Trig. So when you solve for that using Pythagorean, you get 6.708 centimeters, which is 0.06708 meters. Then plus, last guy is 4 microcoulombs, 4 times 10 to the negative 6. The distance here is what? 0.03, right? 3 centimeters. And then punch this into your calculator, and you're done. The answer comes out as 2.67 times 10 to the 6 volts, not to be confused with volts. All right, now part B. Part B says repeat the calculation if this guy is a negative charge. So if this guy were negative instead of positive, would that make a difference? Yep. So all you're going to do is you're going to go right here to this guy, and you're going to make this, instead of that being plus, you put in a minus right here. Stick a minus there. So this was the answer to A. The answer to B, when you change that to a minus, comes out as 2.13 times 10 to the 6 volts. So it's scalar as opposed to vector. If you're asked to find electric potential, you should be like this. You should be like, woo! They could have asked for electric field, which would have wrecked my brain. That's what you say. Electric potential, much easier. Okay, so now, number 13 connects to number 14. So dudes, I'm going to throw up number 14. It refers to number 13, but you know what? I'm going to make a new video here, so we'll